All right, so last time we started talking about principal bundles, and today we're going to spend actually a fair amount of time looking at more examples. So remember that we have the structure group G equals the fiber itself, with the left action of G on itself. And so I remind you that we also showed that principal bundle over a base E is trivializable but only if there exists a global cross-section. That is, we have this pi here, and a cross-section is a map S, so that if I take S and then I apply, if I go up and then down, I get back to where I started. Okay, and local cross-sections always exist, but global cross-sections for a principal G bundle might not. So then we were starting to look at some examples, and so we discussed RPN, where we can think of it as a series of fibrations, where we first divide out by the positive real numbers. We get the n-dimensional sphere, and then we divide out by Z2 to get RPN. And today I want to start with the complex analog of that. So it's essentially the same idea. CPN is the moduli space of complex lines through the origin in n plus one dimensional complex number space. So from that description, we know that we should look at it as C to the n plus 1 minus the origin mod C star. On the other hand, where the C star acts, as I think you all know, as Z1 through Zn plus 1, is identified with lambda Z1 through lambda Zn plus 1. Lambda C star. Okay, and so we would be trying to parameterize the line through the complex line through this point. Good. So now every line is spanned by a unit vector, where we put the natural Hermitian metric on Cn plus 1. And so if we look at the unit vectors, the unit vectors is S2n plus 1. So it's the set of Z, such that Z dot Z star is 1. But that still doesn't uniquely determine a line through Z. We've fixed the gauge, if you will, a little bit by making it a unit vector, but still we could rotate Z by a U1 phase. And so we have a second vibration by U1. So we have an analog of this picture here, where now we have R star plus over we mod out Cn plus 1 minus the origin to get the 2n plus 1 dimensional 2n plus 1 dimensional sphere. I'm trying to get my signs right. And then we could mod out by the extra U1 to get down to CPN. Okay, so as before, these two presentations of CPN each have their advantages. From this point of view, it's clear that CPN is compact, whereas it's not at all clear that CPN is compact when you you look at it from this point of view. Okay? Because, you see, this is a non-compact space, and this is a non-compact group, so you don't know. On the other hand, so that's an advantage of this point of view. On the other hand, there's a brilliant advantage of this point of view, which makes it completely obvious that CPN is a complex analytic manifold. Everything in sight is complex analytic. This is a holomorphic group action on a complex space. So this point of view implies that CPN is a complex manifold. Okay, so comparing these points of view can be useful. Now, once again, I claim that this is a non-trivial fibration. And would anybody like to offer proof of that? Of course, if you've all read the notes, then we know the proof right away. But I suspect you haven't read the notes. There's an easy proof that this is a non-trivial fibration. So, you see, if it were a trivializable fibration, then I would be able to certainly be able to find some diffeomorphism that looks like this. That's the trivial bundle over CPN. I'm claiming you can't do that. And there's a simple reason for that. I asked you an analogous question last time. Last time, remember, I said, well, how do I know that I can't write Sn as RPN times C2?
Not connected.
The answer there was that Sn is a connected space. So, hint, there's a similar line of reasoning here. Not simply connected, perfect, right. So we know that the spheres have 0 lower homotopic groups, and this is clearly, no matter what pi 1 of this is, remember, pi 1 of a product of two manifolds is the direct product of the groups. That's an exercise in the notes from a chapter or two back. So no matter what pi 1 of CPN turns out to be, in fact, it's trivial, but no matter what it was, you get something non-trivial from here. So that's a contradiction. Okay. Now, we start to observe, then, a rather beautiful pattern. If you recollect that that Z2 is the group of units in the division ring R, and U1 is the group of units in C, and then that might suggest to you that, well, hey, SU2 is the group of units in the quaternions. So one way, a nice way of thinking about SU2 is that it is the group of unit quaternions. So, indeed, there's an analogous set of fibrations, again non-trivial, over quaternionic projective space. And quaternionic projective space is just what you think it is. You take n plus 1 tuples of quaternions, and you mod out by a multiplication by a common quaternion, where Q is is an element of H quaternion star, invertible quaternion.
So what is group of units?
What is the group of units? Well, these are division rings, so I can talk about the elements such that QQ bar equals 1 in each of these. They all have a complex conjugation, and so we can talk about the set of XX bar in each of these cases. Okay. SU2 can be thought of as the quaternion such that QQ bar equals 1. So this is the common pattern. Now, something funny happens here because, you know, the quaternions are not commutative. So you could define a left quaternionic projective space and a right quaternionic projective space, but they're isomorphic. Now, given that pattern, there's a natural question to ask. Anyone want to ask it? Yeah.
What about a group of unit Octonians?
Yeah, exactly. So, so could we have some kind of F7 vibration over the 8n plus 7 sphere over OPN? So you might guess that there is such a thing, but that does not happen. No, because, you see, what would you do to define the octonionic projective space? Well, you would have to take n plus 1 tuples of octonions and identify them under multiplication, say on the right, by non-zero octonions, okay, where O is in the star. But the problem here, does anyone see the problem? There's a problem with this. Not associative. You see, this has to be an equivalence relation. Something we often take for granted. But this isn't an equivalence relation because the octonions are not associative, so you're out of luck. However, for n equals 1 is special. And indeed, let's look at the n equals 1 cases here. So n equals, in the various examples here, so n equals 1 gives us, in the first example, over the reals, we have a non-trivial double cover of a circle by a circle. So this S0 you can think of as V2, the zero sphere. In the complex case, we have what's called the Hopf vibration, which we'll talk about in detail in a moment. And then in the quaternionic case, we have a S3 vibration over HP1, and HP1 is the 4 sphere. And it is true that you can make sense of a vibration of S15 over SA. So you have these vibrations of spheres by spheres, which we can associate with the, with the norm division calculus. Now there's actually a nice argument for, I say a little bit about how you do this in the notes. So there's a nice argument for why these don't have global cross sections. Okay, so we already gave some arguments in these first two cases, but yeah, you see with this case, it's not so obvious, right, that this is a non-trivial vibration. Well, it is obvious. Because if it were S3 times S4, if S7 were S3 times S4, then pi 3. Okay. But there's another argument I want to suggest, which is elegant. So supposing there were a cross-section in any of these cases. So let's let S sub t being the dimension of the total space, S sub b being the dimension of the base space, and then S sub phi. So we have vibrations of spheres by spheres. So we have a pi here. We have a putative global cross-section S. And so what I want to note is that, well, having a cross-section means pi composed with S is the identity map. And that means that on the homotopy group, pi sub b of S sub b, we have pi S star. But pi S star, you see, is again going to be the identity map. So this is Z, and we would be mapping Z to Z by the identity map in homotopy. Okay. On the other hand, you see, let me do it this way. So on the other hand, this map factorizes. You see, it goes by S star up to pi sub b of S total, and then by pi star back down to S sub b. But the base dimension is always less than the total dimension. Okay? So this is the zero group. So you would be factorizing the identity of homomorphism here through the zero group, and that's clearly impossible. Okay? You would be going through 0, whereas you're trying to get 1. Okay. So that's another slick proof that that these vibrations are all non-trivial. Now, there's a generalization of projective spaces which you should be aware of because it occurs a lot in string theory. And it's called weighted projective space. And it's denoted P of W1 through Wn plus 1, where for the moment Wi's are all positive integers. And it's again the quotient of Cn plus 1 minus the origin by C star. But now, so you see that looks like that, except now Z1 through Zn plus 1 is identified with lambda to the W1 Z1 through lambda to the Wn plus 1 Zn plus 1. Okay, so we have different powers of lambda here. Okay. And this will again give you a C star bundle over some space, over weighted projective space. But the important thing to bear in mind is that now P of W1 through Wn plus 1 in general is an orbifold. And let's see why that's true. In an example, let's work out P of 1, 1, 2. Okay, so we have W1, W2, sorry, Z1, W's are weights, Z's are complex numbers. So let's look at these. Let's look at the equivalence classes of these gadgets. Okay, and so we have different patches. Okay, so we could take, if Z1 is not equal to 0, then we can fix the gauge. So let me organize it this way. If Z1 is not equal to 0, we can fix the gauge by considering 1, Z2, Z3. Okay, so in that coordinate patch, the gauge is completely fixed. Remember, this is equal to lambda Z1, lambda Z2, lambda squared Z3. Square brackets are the equivalence relation. Okay. So if the Z1 is not equal to 0, I can fix the gauge. And so this coordinate patch is indeed a copy of C2. If Z2 is not equal to 0, same story. Okay? But supposing that Z3 is not equal to 0, okay, then we'll try and fix the gauge by taking Z1, Z2, and 1. Okay, but you see there's a problem here. See the problem? You're on the right track. You're on the right track for sure. Have I fixed the gauge? That's the question.
A rotation of Z1 and Z2 just...
Yeah, you see I have not completely fix the gauge. Because there's still the freedom to identify this with minus Z1, minus Z2, and 1, because minus 1 squared is 1. Okay? So this patch is C2 mod Z2. Okay. So you see this thing is an orbifold, not an actual manifold. And now you can imagine that if you choose various weights, play around with it, then in different places you can have different orbifold singularities by different stabilizer groups. So I gave you an example of a very simple orbifold earlier in the course. I simply said, well, take Rn mod gamma, right? But here, you see in different parts of the manifold, you have orbifolds by different groups. Okay, so this is an interesting example. Okay, so now that was my first set of examples.
Before you read the examples, regarding the 4 different sphere vibrations.
Yeah.
For the last one, you said that sense can be made of that vibration.
Yes, that's right.
In what way, though, does it relate to octonions at all? Because you wrote.
Oh, it definitely uses the octonions. Look in the notes. It uses something called the Cayley plane. So the S15 is what you do is you take a product of the octonions times the octonions minus 0, and then you indeed can divide that by 1 copy of the octonions. And so you can get around this problem of non-associativity, but you can't generalize that. Okay, so I now gone through one set of examples. I want to go through a related set of examples having to do with homogeneous spaces. So so supposing that G acts transitively on M, okay, then every point has a stabilizer, and the stabilizer of any point, of some point, P will be some subgroup H in G. Now, as you change the point, you'll get conjugate subgroups. And you can identify this M here as G mod H. And if the G's and H's are compact, there's not going to be any problem here. This will be a nice manifold. And in fact, what we get is a principal bundle, a principal H bundle with total space G over the set of left cosets G mod H. And there's an exercise here that guides you through proving that using definition B of a principal bundle that we discussed last time. Now, another preliminary before I go discussing the examples is I just want to remind you of the relationship between ON and SON. Okay, so ON differs by SON by a Z2. And this sequence splits when n is odd. And that's n odd. And it's a non-trivial extension. It's a semi-direct product when n is even. And similarly, SUN maps into UN, and the quotient is U1. And again, this is a non-trivial extension. So UN is equal to SUN times U1 mod ZN, where the ZN is embedded in both. In fact, that's another example of the principal ZN bundle. Okay, so now let's apply this remark here to the spheres. So in these previous examples, spheres were the total space of a bundle. Now it's going to be the base space. So let's take the unit sphere in Rn plus 1, and this has a transitive On plus 1 action on it, right? This is a transitive ON plus 1 action, so it's a quotient of ON plus 1 mod H. And what would H be? First of all, you all see that as a transitive ON action on this, right? Yeah, okay, good. So how would you calculate the stabilizer of a point? Okay, I recommend that you choose a simple point, right? You don't choose some unit vector, or, you know, choose this point. Okay. What's the stabilizer under ON of that point? ON, right. So it's got to be an ON matrix that looks like 1, 0, 0, and then an ON matrix. Okay, so SN is ON plus 1 mod ON. Now, it's also true that it admits a transitive SON plus 1 action, right? You don't need the orientation reversing transformation to map any point on the sphere to the North Pole. So now what would the stabilizer of the SON plus 1 action be?
SON.
SON, right. Okay, so you see that we can write the sphere as the base space now of a principal ON or SON bundle. And roughly speaking, the Z2 factors are canceling out there, very roughly speaking. All right, well, let's do the same thing with the odd spheres. So if I consider S2n plus 1 as the set of Z such that the Z dot Z star equals 1, well, you see that has a transitive UN plus 1 action. Okay, and again, by the same kind of reasoning, its stabilizer is UN, and similarly, it's also got a transitive SUN plus 1 action, which SUN is as the fiber, and we can also do that for the symplectic group. And so the common story then is that UN over RC or H into UN plus 1 over RC or H is a sphere, C to the S to the C times n plus 1 minus 1, where C of F, a convenient notation to introduce, is the dimension over the reals of this norm division algebra, 1, 2, or 4, for F equals R, C, or H. And I should say that UF, in this notation, UF of n is ON, UN, and USP 2n. So you can think of USP 2n, I tend to think of it in terms of the unitary symplectic group of 2n by 2n matrices, but another way of thinking about it, which makes it uniform in these descriptions, is to think about it as the n by n unitary matrices over the quaternions. Okay. Oh yeah. So it's kind of interesting that we have this pattern here of SUN to SUN plus 1 over SN plus 1. And just as a little side remark, you might think then that is SUN, or SUN plus 1, a product, quotes, of odd spheres? Right? Because you might say, well, okay, at least naively, I might try and write SUN plus 1 as SUN plus 1 divided by SUN times SUN divided by SUN minus 1. I hope you realize this is being very heuristic. SUN minus 1 by SUN minus 2, and so on until you get down to SU1, and SU1 is a point. Okay, and then this is a 2n plus 1 sphere, and this is a 2n minus 1 sphere, and so on. And in fact, that's true, in a sense. So it's true rationally. In other words, in rational cohomology and in rational homotopy theory, in fact, it's true that you can't distinguish, if you're thinking about homology over the rationals, or homotopy theory, you can't distinguish between a special unitary group and a product of odd spheres. And so a way of thinking about the special unitary group is that you're taking products of odd spheres, but they're not quite products. They're twisted products with a torsion kind of twisting, a very subtle twisting, which you don't detect rationally. Okay. In the notes, you can combine this. You can combine these decompositions of these presentations of spheres as base spaces, but the spheres as total spaces, to get the complex projective, the projective spaces as themselves homogeneous spaces. So if we combine the two examples that we just saw, then, for example, we'll find that un times u1 goes into un plus 1 and projects down to CPN. And we can also take this and put an S here, and so that is a way of presenting CPN itself as a homogeneous space. And similarly, ON can be embedded into SON plus 1, and it projects down to RPN. Now, do you see how you can embed ON into SON plus 1? Or SON plus 1 has determinant minus 1. But ON can have determinant plus 1 or minus 1.
It's just a guess, but if you subtract the trace from on the algebra level, would that work?
Well, something like that. You're thinking in the right direction. So if you have A and ON, then you embed it as 1A if the determinant of A is 1. But you embed it as minus 1A if the determinant of A is minus 1. So you see, those are SON plus 1 matrices. That's a group embedding. Okay, so you see there's this funny business with Z2, and that funny business is just right, so that if you combine the two examples I had, you'll get this homogeneous space presentation of RPN. Right. Okay, so now we're going to look at one example of these in gruesome detail, because it's such an important example. And that's the case of the Hawk vibration, where we have a one-dimensional sphere fibering over the two-dimensional sphere to give a three-dimensional sphere. Okay, so we have S1 embedded into S3 over CP1, which is S2. Well, let's just leave it as CP1 for the moment. And I guess I was emphasizing that it's U1 here. Okay, so as we've seen, we can think of this S3 as the set of alpha and beta, such that alpha squared plus beta squared equals 1. Before I go into all the details here, why am I going to beat this to death? Because this example is really important in physics. It's at the heart of the magnetic monopole, but it comes up all over the place in one example after another, and it's just good to have this example really firmly in hand. Okay? So we're going to go into it in detail. Okay, so we've seen that this CP1 is obtained by identifying alpha with e to the ix, alpha beta with alpha e to the ix, beta e to the ix, phase. The equivalence relation, that's the equivalence relation that defines CP1 if I impose this condition on alpha and beta. On the other hand, as I was just saying, we can identify S3 with SU2. And how do we do that? Well, to alpha and beta, satisfying this condition, we associate the SU2 matrix given by that equation. Okay, so now let's embed a U1 into SU2 by saying that that U1 subgroup is the group of matrices e to the minus I over 2 sigma 3 chi, where I'm identifying chi with chi plus 4 pi. So it's my choice how to embed U1 into SU2, and this is how I'm going to do it. So now think about our definition B of a principal U1 bundle. We want a smooth right fixed point free action of U1 on SU2. So we have our right U1 action on SU2 by these matrices. So alpha beta minus beta bar alpha bar goes to, under this action, alpha minus beta bar beta alpha e to the minus I chi over 2 e to the I chi over 2. And now you see if I work out what that is in terms of alpha and beta, that's alpha and beta goes to alpha e to the minus I chi over 2, beta e to the minus I chi over 2. So that's exactly the kind of equivalence relation we use to define complex projective space. And because alpha squared plus beta squared is equal to 1, they can't both be 0. Okay? Okay, so putting it this way, we are thinking about our bundle as a homogeneous space vibration. And we see that these two vibrations are exactly the same thing under the equivalences I just wrote. Okay, now there's another way of identifying this homogeneous space with the two-sphere, where I'll think of the two-sphere as the unit sphere inside Euclidean free space. And the way I do that is I say pi of g is equal to the vector x, where g sigma 3, g inverse equals x dot sigma. So that's something I think you all know from quantum mechanics. Right? Okay, and as you all know from babyhood, you can define polar angles. Sine phi, sine theta, cosine phi. And if you introduce polar angles that way, then you can find a g that projects to this x, and that g is equal to e to the minus I over 2 phi sigma 3, e to the minus I over 2 theta sigma 2, e to the minus I over 2 psi sigma 3. The signs drove me absolutely crazy preparing this, and you should check me. I think these signs are correct. So you can decompose G. You can write a group element in this way, and then you can check that if you work out this conjugation of the Pauli matrix sigma 3, which you should think of as corresponding to the north pole, then this will rotate down to the point theta and phi. Okay, so now if you multiply this out, you'll get an alpha beta minus beta bar alpha bar, where alpha is e to the minus I psi plus phi over 2 cosine theta over 2, and beta is e to the minus I psi minus phi over 2 sine theta over 2. So one more thing to say is that these coordinates are, of course, now related to stereographic projection.
Sorry, what is psi?
What is psi? Psi is right here.
But it's not the polar coordinate.
Absolutely correct. Very crucial remark. So this is the projection from S3 down to S2. This x is in S2. What is the fiber of that projection? Thank you for asking this question. I should have said this. What is the fiber of that projection? It is the group psi. It is the U1 subgroup generated by this. You see, because I chose sigma 3 here, that guy cancels out. Now notice that that's precisely the right action. That's why I chose that embedding of U1. That's the right action, which is supposed to generate for me the fiber. Okay? So, indeed. Now what you should be thinking, now what is a choice of cross-section of this principal bundle? A choice of cross-section of this principal bundle is choosing up psi uniquely and continuously for every theta and phi. Or better to say, for every point on this sphere, your local cross-section is choosing up psi given a point on the sphere. Now remember our theorem. If you can do that globally in a smooth way, then you have trivialized the bundle. On the other hand, we made some elementary observations that showed that it's not a trivial bundle. So something has to go wrong. And we'll see in the formulas what goes wrong. Okay, yeah, just one more thing to set up here is, this is often useful to think about, is stereographic projection. So, so we're going to think of the unit sphere, which is now being either projected from the South Pole or the North Pole. So this projection is P from the North Pole, and this projection is P from the South Pole. So in formulas, P south of x is x1 over 1 plus x3, x2 over 1 plus x3. So you see, if x3 goes to minus 1, which is the South Pole, then your point goes off to infinity. And P north of x is x1 over 1 minus x3, x2 over 1 minus x3. So that if x3 goes to plus 1, which is the North Pole, the point goes off to infinity. Now, okay, so that defines projections, P south and P north, define projections from S2 to R2. But now here comes the tricky point. I want to identify R2 with the complex plane. Okay, so let me put it this way. Should I identify x1 plus I x2 over 1 minus x3? Or should I identify x1 plus I x2 over 1 plus x3 with a point in the complex plane? Which one? Is it okay to do both? Let me point something out. This, now remember, the sum of the squares of the x's is equal to 1, right? So if I multiply and divide by x1 minus ix2, okay, then in the numerator I get 1 plus x1 squared plus x2 squared, which is 1 minus x3 squared. So I get 1 plus x3 over minus. Okay. Now notice that this is 1 over the complex conjugate of this. So they are not mutually holomorphic. Okay? Now you've got to make a choice. You've got to make a choice here. You see, what's going on here is that the complex plane has two inequivalent complex structures. Okay? So I'm going to make a choice. And the choice I made is that we have z south bar here and z north here. So in terms of the polar angles, this is tangent of theta over 2 e to the I phi, and this is cotangent of theta over 2 e to the I phi. So notice the complex conjugate. And I made that complex conjugate choice so that z north equals 1 over z south on the overlap region. So good. So in terms of CP1, if I look at an equivalence class of alpha and beta, that's equal to alpha over beta 1, which is equal to z south 1 on the southern hemisphere, US. Okay, the southern hemisphere is the sphere minus the north pole. Okay? And similarly, this is equal to 1 beta over alpha equals 1 z north on u north, which is S2 minus the south pole. And in terms of polar angles, US is the set of theta and phi such that 0 is strictly less than theta, less than or equal to pi, and this is theta and phi, so that 0 is less than or equal to theta, but strictly less than pi. Okay. With those preliminaries in hand, we can now construct our bundle. Are there any questions? Okay. So on u north, we have cosine of theta over 2 not equal to 0. So you see it's crucial that I have theta less than pi on u north. So cosine theta over 2 is less than 0. So now if I go back to my alpha and beta, you see I can unambiguously extract the phase e to the I psi plus, this phase here, e to the I psi plus phi over 2. I can't unambiguously extract this one because if theta equals 0, the sign is 0, and this phase becomes ambiguous. I just don't know what it is. If a complex number is 0, you just don't know its phase. So we can extract e to the I over 2 psi plus phi. Good. So now we introduce a trivialization from pi inverse of u north to u north times u1, which is given by phi north of our SU2 matrix is x hat, that's well defined, e to the I chi north, where chi north is psi plus phi over 2. Okay, so that's well defined. And we do the same thing on u south. Now sine theta over 2 is not 0. So we can extract e to the I sine minus phi. So we define trivialization I hope nobody's confused about the two phi's. This is a trivialization, that's a polar angle. This is phi sub south is phi inverse of u south to u south times u1 given by phi south of g is x hat e to the I chi south, where chi south is psi minus phi over 2. And on the overlap region, the North Pole intersect the South Pole, we can calculate the transition function. Phi south, phi north inverse of x hat e to the I chi north is x hat e to the I chi south by definition. And by definition of transition function, this is g sub south north, which is a function of x hat, times e to the I chi north. That's how we defined our transition functions. I'm using exactly the notation that I used in the general definition. So you can see the general definition explicitly in this important example. Okay, well, now you look at those formulas over there, and you see that e to the I chi south is g south north times e to the I chi north, and g south north is e to the minus I phi. Okay, so now we have constructed our bundle. So over the equator, or as long as phi is well defined, we're gluing our two copies of u1 in a way that depends where we are on the sphere. And as we go around the sphere, we change that gluing identification of the two fibers exactly in this way. And you see that this has an interesting winding number. There's a sphere here on the equator, and there's a sphere in the space of transition functions, and there's a winding number 1. And that is indicative of the topological non-triviality here. Just to really nail it down, let's also look at the local cross-sections, okay? So, can we find cross-sections? In other words, can we take an x hat and map it unambiguously to a group element, which, by this formula here, projects back to x hat? And why not, you say? Okay, give me a phi and a psi. I'll give you a theta and a phi, and just make some choice. But what's wrong with that? I mean, didn't I actually trivialize the bundle when I wrote these formulas? Right? I mean, if you have a theta and a phi, you know where you are on the sphere. You take that theta and phi, you write this alpha and beta, make some choice of psi, anything you want. Haven't you trivialized the bundle? Well, you don't have a phi all the time, exactly. So we can make a choice. So let's call it S sub north, as long as, so on the North Pole, theta can go to 0. Theta can go to 0. When theta goes to 0, as I said, this is non-zero. So you're going to have a problem with this here. Okay. So a natural way to choose a section on the north hemisphere is to, this is not the only choice, but a natural choice is to make psi plus phi equals 0. In other words, psi equals minus phi. So good. So you do that, and you get cosine of theta over 2 minus e to the minus I phi, sine of theta over 2, e to the I phi, sine of theta over 2, and cosine of theta over 2. Okay, so now I've made an explicit choice of cross-section, but only on the north hemisphere. Continuity is really important here. Okay? So you might say we don't know what phi is at the North Pole. It's true. We don't know what phi is. Is that a problem for this cross-section? Well, no, it's not a problem. Why not? I mean, I wrote phi, but phi is not well defined all the time. So why is that a problem? I claim this is continuous. Because the sign is going to 0. Exactly. So in fact, this is a continuous map. Even though I wrote phi, phi is illegal. Even easy I phi is illegal. But the sine theta is killing it. Exactly at the bad place. So this is continuous. Okay. So, same story on the South Pole. On U south, we write section south takes x hat to e to the minus I phi cosine of theta over 2 minus sine of theta over 2 sine of theta over 2 e to the I phi cosine of theta over 2. And what I've done here is I've made the choice sine minus phi equals 0. And same story here. So I don't know what phi means at theta equals pi, but that's okay because the only time it enters is when it multiplies cosine theta over 2, which vanishes at the South Pole. So this is also continuous on the South Pole. Now, I told you in definition B of principal bundle that we compare the local cross sections and see what the right action is, right? We started from the very beginning. I said we have SU2 here, and we have a certain right action of U1 on SU2. Okay? So therefore, the sections should be related on the overlap. So on U north intersect U south, we have S north of x hat equals S south of x hat. Now notice with a right multiplication times e to the I phi e to the minus I phi. Okay? And from that, we can again extract our transition function. E to the I phi. Okay. Are there any questions about that? Okay, one last example of a homogeneous space, which comes up in physics. Good bit, yeah.
Could you give me some visualization of this Hopf map?
Sorry?
Can you draw a picture of this Hopf map?
Oh, yeah, great question. Really great question. Yeah, in fact, I meant to say that. Yeah, try to write this, try to visualize this Hopf vibration. And try it with the following question, which is an exercise in the notes. So, so the total space, well, it's right here. So the total space is a 3-sphere, and the fiber is U1, but let's think of it topologically as a one-dimensional sphere. So now let's take 2 points, P1 here and P2 here. Okay? So the fiber here is some circle, and the fiber here is some circle. And so that means I have 2 circles embedded in the 3-sphere. Now, think about it. If you have 2 circles embedded in the 3-sphere, well, choose some point which is not on those 2 circles and stereographically project into R3. Okay. So that means I have 2 circles in the room here. Okay? R3 is the room. Now, question. Do they link or do they not link? Well, the way I drew it looks like they don't link. But I'm not a good artist. So, if you want to get a visualization of the Hopf vibration, I encourage you to think about that question. All right. One more example. So, again, it's a uniform discussion for F equals R, C, or H. If you're scared of H, just think of R and C. If you're scared of C, think of R. So the Grassmannian GR sub Kn, or if I want to emphasize F, like that, I'll write both, is the moduli space of K-planes in Fn. So we've met this already in the case k equals 1. So a K-plane is a K-dimensional K-dimensional space to the origin. And if k equals 1, that's our projective spaces, our moduli spaces of lines. Okay? So we're generalizing complex projectives, or we're generalizing projective space, the space of lines. Now, how do we see this as a homogeneous space? So let's introduce V sub k, non-compact of Fn, to be the set of all k by n matrices of rank k. Okay. So you think of this, an element in this lambda, it's an explicit k by n matrix, so it's v11 through vk1 through v1n through vkn. And you say, okay, the rows of this matrix are vectors in n-dimensional space. I have k of them. And so they span, those k vectors span some linear subspace. And if I demand that this has rank k, that implies that the rows span a k-dimensional space. Okay. Now, of course, if I'm only asking about the moduli space of k-planes, I don't care about what basis I use, right? I can use two different bases and get the same k-dimensional space. I'm simply saying take the linear span of these k vectors. So there exists an action of GLK F on this VK compact. Okay, so our Grassmannian is GLK left action on VK not compact. Okay, now there's also a right GLN action, or I'll write it as a commuting left GL action. Hope I don't confuse you by that. And what I mean by that is the following. You see, if G is in GLN, then we can take lambda goes to lambda G inverse. Now I called it a left action because it is a left action because I put the inverse here. If you don't like that, make it a right action. Now, this commutes with the left GLK action, and so there's a well-defined action on the equivalence classes here. On the other hand, so we could just divide out by that. On the other hand, GLK times GLN with this action acts transitively on DK non-commutative, non-compact of Fn. Okay, so I have this GLN action, and it acts on this VK, and it's transitive. And why is that? The reason is that the only invariant of a linear transformation is its rank. So under this, if I have any lambda, that means that I can find an H and a G inverse that puts it into the following form. 1 through 1, and then 0. So this is K, this is K, this is N minus K. There's only one invariant, N is bigger than K. So there's only one invariant of a linear transformation, its rank, and so that means that the action is transitive. Okay, now what's the stabilizer? So the stabilizer is GLK times GLN minus K. You see we have A acting on 1, 0, and then A inverse, 0, 0, B, stabilizer. And so we get that the Grassmannian of K planes in N space is GLN. I wrote it on the right. Strictly speaking, I made a left action, so I should be writing it on the left. Okay, so the Grassmannian of K planes in N space is this homogeneous space. Now we could have taken orthonormal vectors to span our plane. The analogous thing we did in the complex projective space was I said, look, you can always choose a unit vector to span your line. Right? And then I had a quotient of the sphere. So in that way, and I'll skip the details, it's an exercise, you show that we have this quotient. So as before, you see in the complex projective, in the complex case, if I use C, then this is clearly a complex variety. This is clearly a compact variety. And so the Grassmannian is some compact complex manifold. Same kind of reasoning. Okay, so then there are generalizations of this. So this is what the Grassmannian is. It's got several interesting uses. We're going to be seeing a lot more of the Grassmannian in its uses of topology. Let me just mention that there's a further generalization of the Grassmannian. So the Grassmannian is the moduli space of k-dimensional subspaces. Well, you can also generalize this to the idea of a flag. So a flag is a sequence of subspaces. Here, let me two-step flag. Okay, where the dimension of V1 is say K1, the dimension of V2 is K1 plus K2, and then the dimension of the total space, V3, is K1 plus K2 plus K3. So what we had before was V1 sitting inside V2, which was C to the n dimensional, and this is K dimensional. Now I'm saying, let's think about a subspace sitting in a subspace sitting in a total space. Okay, so the picture might be that you have some plane, and then inside that plane you have some line. Okay, a line and a plane in the total space. And so you can do that at these different dimensions, and that's an example of a flag. Okay. So let me ask you to, any guesses as to, that's, again, you can argue that there's a transitive action. First of all, you can choose orthonormal bases for these. So let's do it in that way. You can choose orthonormal bases. You choose an orthonormal basis for V1. You take a complementary orthonormal basis to complete it to an orthonormal basis for V2. And then you take a complementary orthonormal basis for the rest. Okay. Now, you can argue that there's a transitive action of UN on this space of flags. And so it's a homogeneous space. And what do you think it is? It's UN mod UK1 times UK2 times UK3. So to prove that, I would suggest that you think about a particularly nice flag and calculate its stabilizer. Now you can clearly go on, right? You can make the flags longer and longer up to a point. At each step, you have to add an extra dimension in your flag. So the best you can do is a one-dimensional space and a two-dimensional space and a three-dimensional space all the way up to your n-dimensional space. Okay, that's the maximal flag you can have. And that's a full flag. And so the flag variety is the moduli space of these gadgets. And so what is that as a homogeneous space? Well, let's take a particular flag, okay? So let's let V1 be the span of E1. So EI will be the vector 0 with an I, a 1 in the ith place, and 0 else. Okay? So V1 is the span of E1. V2 is the span of E1 and E2. V3 is the span of E1, E2, and E3, and so forth. So that's a particular flag. Okay? And I'd say you can always rotate. You can always, that's the spectral theorem, right? You can always rotate any orthonormal basis to look like that. Okay, so you shouldn't be so surprised when I tell you that UN has a transitive action on the space of flags. You know that you can always take any orthonormal frame and rotate it to this one. Now, what's the stabilizer group of this?
Upper triangularizable. Upper triangular. Maybe?
No, it's got to be unitary. We're in the unitary. So the new unitary group is acting on this flag, okay? So I don't want it to budge the flag, right? I want the isotropy group. So what unitary matrices act on these vectors and preserve the flag? The flag, not the vectors, the flag. So you think it's just Z, that's a scalar matrix, where Z is a phase? That is a rotation, but, so just U1? So you're telling me that the full flag variety is equal to UN mod U1?
Oh, could it be UN cross SU2 cross SU3 cross and like on that?
Okay, so the SU2 is, you want to sort of
you
have
can
a,
rotate like B2 into
you want
itself,
you want an
rotate-
SU2 matrix on this?
Yeah.
But that would destroy the flag, you see.
Oh,
Because it would
then-
rotate the U1, the E1. I can't move. I can only, I have to preserve the line, V1, the space V1, not the vector, the space V1.
Right.
So it's the product of U1 and U1.
Very good. So it's Z1, Z2, down to Zn, where the Z's are phases. So that, you see, it doesn't preserve the vectors, but it preserves the flag. This phase Z1 rotates the E1 to be sure. But you know, we modded out by that before when we did the complex projective space, right? We didn't care. That's why we modded out by V1. Okay, so similarly here, that preserves the vector space V1. And if I want to preserve V1 and how the V1 sits in V2, then it has to be diagonal. And so the full flag variety is UN mod U1 to the n. In other words, U1 modulo, or UN modulo the maximal commutative torus. That's a very important variety in representation theory. And it turns out you can construct all of the unitary irreducible representations of UN by thinking about sections of bundles over this space. Maybe I'll mention more about that next. Certainly not next time, but later on. Okay, so Wednesday next week, I won't be here. There won't be class, but there will be class Monday. Okay, and on Monday, we will continue, and I'll tell you a few things about what goes wrong, or what can go wrong, when you divide out by a non-compact group. So here we've been blindly dividing out by GL, KC, and some of these Grassmannians and complex projective spaces, blindly dividing out by non-compact groups. And so we'll see a little bit about what can go wrong and how you can avoid those things going wrong. That's the first thing we'll discuss. And then we'll classify bundles on spheres. Yes, sir?
If you could briefly give a definition for variety. I don't know if it is.
Oh, I just mean an algebraic, a complex manifold where the transition functions are rational functions.
Oh.